before we dive into it, I wanted to say something about the schedule. Just I'm going to try to keep this as regular as possible. You should expect your quizzes to be, in general, to be due at 11:59 p.m. on Tuesdays, as in last night, and Fridays. When I post them, in theory, you will be able to do it, right? However, if it were me in the class and I wanted to maximize, because you'd be able to do it when I post it, but it's possible, it's not always true, but it's possible that the next day might help a little bit. So if it were me doing it, I would be taking the Tuesday quizzes sometime after class on Monday. And I'd be taking the Friday quizzes. Well, I'd probably take them. You could take them earlier, but if it were me, I'd wait till Friday afternoon or after class to take it if that's possible. Okay, any questions? Okay, so we were talking last time about the equation AX equals B, where A is some matrix and this. By the way, somebody remind me, what is this, when I write this, what does this notation mean? A is in R, M by N.
A is an element of any M by N.
A is an M by N matrix, that's right. The R means that its entries all in real numbers, M rows and columns. So the following conditions for any matrix, any rectangular matrix, the following conditions are equivalent. What do I mean when I say the following conditions are equivalent? What that means is for any given matrix, all four of these statements are either true or they're all four false. Right. So the first statement is for every possible B, this has a solution. So no matter what B is, I can find a solution. If that's true, then it's also true that each B is a linear combination of the columns of A. We saw this last time because we can recouch this matrix equation into a vector equation depending on the columns of A. This also means since every B is reachable, right? Every B is a linear combination of the columns. That means that the columns span every Rn. That means that every possible vector in n-dimensional space is a linear combination of the columns, which means that the columns span it. And last one is a real workaday one. It means that every AX equals B always has a solution if A has a pivot in every row. All right. So what does the last condition tell you about the matrix itself? Right. So suppose that I have an n by n matrix, and suppose for all what does that tell me about the shape of the matrix? It tells me something more than just it being rectangular. What does that fourth condition say?
Square.
Yes, if it's square, that'll work, but you can actually do a little bit better than that. It has to have. How can you compare the rows and columns? If you have a pivot in every row, what does that tell you about the rows and columns? To have a pivot in every row, then what's the relationship between the number of rows and the number of columns? For example, let's look at this. What if I have a matrix that looks like this? And Noah, you were actually, I think, on the right track there. Look at this matrix here. What do we got? I guess that's what, 4 rows, 3 columns? Is it possible, if this is A, no matter what numbers I put in the box, is it possible for AX equal B to have a solution for everything? No. Why not?
It's not a columns.
Well, if you're gonna have a pivot in every row, you'd have to have one here, here, and here. These would have to be pivots. And I've run out of real estate. I can't do it, right? Because the pivots have to occupy different columns. Right? So what does this say? If this is true, if for every B, AX equals B has a solution, what does that mean? That means that the number of columns, how do we compare them? Number of rows.
They're equal. Greater.
Well, what about this one? A without it, what if it's this? Is it possible to have a pivot in every row now? Certainly, right? I mean, you can't have one in every column. But if you did sort of the same thing we did before, now you've got a pivot in every row. Right? And according to this theorem, that means that this will have a solution no matter what. Do I agree with that? So, what does it say about the number of columns versus the number of rows?
Column is greater than the 2.
That is correct. The number of columns, so if this always has a solution, then the number of columns has to be greater than or equal to the number of rows. And notice what happens when it's equal, you get the square case we talked about earlier. Am I okay with that? Okay. We're gonna get our hands dirty later, but I'm gonna go over a couple of so here's kind of the next theorem, and then I'm gonna give you sort of a big theorem, and we're gonna spend some time looking at how to do that. There. Okay, so again, suppose we have a rectangular matrix, M rows and N columns. Okay, so let me break this down. What does all this math code say? A is an M by N matrix. These are N by 1 matrices, so these are just vectors, right? U and V are just N column vectors, and C is a real number. Then, number 1, what do you suppose this is? What do you hope it is?
Multiplication.
Yeah, I mean, I hope it distributes out, and it does. And what happens when you take a matrix times a constant, multiple a scale of the vector? You can pull that C out. Let me actually, I'm going to take a minute and I'm not going to go through this because the details are, if you want to actually try to prove this for yourself, then good for you. And it's not too terribly difficult. I'm going to do some kind of more practical computations here. If I have A is, um, what's this matrix? What size is it? It's, this is in R, what by what? Agree, 2 rows, 3 columns. What size does you need to be for me to be able to actually do this?
3 by something.
3 by 1, right, well, 3 by something more general if it's a matrix, but yeah, in this case, let's go 1 minus 1 minus 2. It has to be 3 by 1. And when I multiply this, what should it barf out? Right, it should be a cancel of 3's 2 by 1. Do I agree with that? So we saw how to multiply this. And the way we did this was sort of column wise, and this is the connection between this matrix equation and vector stuff. This should be 1 times 2 minus 1 should be minus 1 times 3, 4. And it should be minus 2 times 1, 7. So first entry times this column, second by this column, third by this, which gives me 2 minus 1 plus minus 3 minus 4 plus minus 2 minus 7. That should be 14, of course. And this comes to the vector minus 3 and minus 19. Do I agree with that? Now, there's a more general way that you could do this. And I'm going to do this by example. We're going to talk about this later. But what if I multiplied this by a, this is a 2 row by 3. How'd you say it, William? A 3 by anything? Okay. Let's go 3 by 4. I need, let me just make a 3 by 4 matrix. So I need 3 rows and 4 columns. So I've got 4 columns here. So let's go 1, 2, 3, 4, 5, 6, 7, 8, and minus 1, minus 3, minus 1, minus 2. Now, when I multiply these two, I should get a 2 by 4 matrix. 2 rows, 4 columns. And how do I do this? Well, to get the first row, first column entry, just take the first row of this, multiply by the first column of this, piece by piece. What's 2 times 1? 3 times 5 is 15. So I'm up to 17. 1 minus 1, that's 16. Are you okay with that? What do so I need first row, second column, first row times second column, and I do the same kind of procedure here. This times this piece by piece. That's going to be 4 and 9 is 13 minus 3 is 10. Everybody follow what we're doing here? Okay, let's keep it going. First row, third column, this times this. That's going to be 6 and 21 is 27 minus 1 is 26. And finally, 8 and 24 is 32 minus 2 is 30. So there's my first row of the new matrix. Everybody okay with that? Same procedure to get the rest of it. This row comes, this column will give me my second row, first column. So that's going to be -1 and 20 is down to 19, down to 12. For here, I'm gonna have -2 and 24 is 22, -21 is 1. Get -3 and 28 is back down to 25, -7 is 18. And finally, -4 and 32 is 28, -14. Everybody see how we did that? Yes, sir.
Did you do first row, second column, correct?
Maybe not. Let's see, -2 and 24 is down to 22. Minus-
First row,
Oh, I'm sorry, first row,
yes, sir.
-1, that's 20 -1 is 19, minus another 7 is 12, right? Did I get it right?
10.
Are we talking about this one?
Yes, sir.
Okay, well, let me figure out, what is this? First row, second column, so let's go back and check that. First row, second column, let's see if Jim messed it up. It's gonna be 4 and 18 is 22, -3 is 19. What did I have, 10? Absolutely. Did you catch any other mistakes? Who knows, right? Everybody okay with that? Okay. Now, we are going to look at. So what we've looked at so far is we have. We're going to solve some of this in a bit, but. If B is the zero vector, then this equation is homogeneous. So if I say a homogeneous equation, it's the special case when the B vector is zero. Now, you might say, well, Jim, what in the world are you doing, right? I mean, we've already done it for B. Why would you now just put the brakes on and go back and look just at the zero case? But the zero case is actually very important. And you can build all the solutions off the zero case in a particular solution for the other one. How many of you have been in differential equations? Obviously, this is not necessary, but you probably saw this with particular solutions and you add some other stuff to it. This is very similar here. It turns out that this thing right here is the seeds and helps us understand the more general equation. Now, one of the things that's different about the homogeneous that gives it a slight advantage to this one is this one may or may not actually have a solution. It's possible for this to yield an inconsistent system and you've got a solution. However, the homogeneous equation, that baby's got a solution. Somebody tell me a solution to the homogeneous.
Zero vector.
Zero. Zero for sure is a solution to this. This is always a solution to the homogeneous. So with the general equation, you have to worry in the first place, well, is this even consistent? Does this even have a solution? This one, the worry is gone. And your question is now reduced to two things. It's got a solution. One solution for sure is a zero vector. One of two things have happened. It's either got a unique solution, in which case the zero vector is the only solution, or it's got infinitely many. And it depends on whether Friedler will show up when you reduce it. So let me give you this big kind of computational theorem, and this is the importance of the homogeneous. I'm gonna demonstrate why it's true, and then we'll get our hands dirty here. So, there. Suppose AX equals B is consistent. And as I pointed out, for the general equation here, that's the big first out of the gates question that you have to ask. Does this even have a solution? Let's assume, just for giggles, that AX plus B actually has a solution. And let S be any pollutant. Okay, so if AX plus B is consistent, then it's got some solution. Let S be any solution. I don't care which one. Maybe there's only one, maybe there's infinitely, but there's at least one, so pick S at random. It's any solution you like. Then any other solution to AX plus B, or I'm sorry, AX equals B, can be written as S plus U, where U is a solution to homogeneous equation AX equals C. So what this theorem is telling me is this. If I have a consistent system, AX equals B, all I have to do is capture one solution, whatever solution I can capture, S, and any other solution to that equation, all of them, can be written as that S plus a solution to the homogeneous, which is often easier to find, right? In fact, let me point out, one solution to the homogeneous equation is always zero, right? If you let U equal zero, you get your original S back. But any other solution is S plus perhaps something other than zero. This is perhaps not obvious. Why is it true that if I pick a solution at random, any other solution is a homogeneous plus this? Is it clear? Can anybody explain that to me? Oh, good. That's what I'm for. So let's see why that's true. One of the reasons I want to prove this for you is because it's easy. And I am a lazy man. Suppose S is a solution to AX equal B. So what does that mean? That means if I plug in S for X, it works. Everybody agree with that? Let Z be any other solution. Pick one at random. What does this mean? This means that AZ is also equal to B, right? Because it's another solution. Everybody agree with that? And this, of course, was also equal to AS. Right? So AZ is equal to AS, right? So I can subtract them both from, so A is the zero vector. Everybody agree with me? Uh, actually, I meant to write it this way. But it doesn't matter. I can just subtract AS from this side instead of, or I'm sorry, AZ from this side. Everybody okay with it? Can anybody see a way I can simplify the left side of that equation?
Factor out A.
That's right. That's one of the things that we just learned. This factors out A. What does that mean about S minus Z? And actually, I did this up again, but I want to do it the other way. S minus Z is a solution to AX equals 0, right? And so is Z minus S, right? If I had subtracted the other way, like I did in the first place. Everybody okay with that? So, watch this. My Z is my S plus the solution to the homogeneous, right? So, not too bad. But even though that might seem silly, it's actually very important because it helps us parameterize general solutions to the equation AX B. So let me start off by, let's do some examples here. Any questions? Yes.
Could you explain that last part you just talked about? Z equal.
Because remember what the theorem says is any solution can be written as the solution we picked, which was S, plus the solution to the homogeneous. Well, here's the solution we picked, and up here we notice that this is the solution to the homogeneous. Okay, other questions? Okay, so let me let's do the following matrix here. Let's let A 1, 5, minus 1, 4, minus 3, minus 5, minus 18, 3, minus 11, 4, 7, 24, negative 4, 15. Okay, so of course, I could also think of this as a system of equations, right? X1 plus 2x2 plus 5x3 minus x4 plus 4x5 equals 0, and so forth and so on. I want to find I want to find the solutions. Now, in all the problems that we've done before, I always augmented the matrix, right? And put, because x1 plus 2x2 plus 5x3 minus x4 plus 4x5 equals 0, blah, blah, blah equals 0, blah, blah, blah equals 0. Why didn't I augment the matrix this time?
It's equal to 0, so there's no like right side of it.
I could put dot, 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 0, 0, 0, right? Do I agree with it? I could. But then every time I do these row operations, nothing's going to change in that 0 column, right? And so let's not make it more difficult. I often do the augmented matrix without the dot, dot, dot solutions when it's homogeneous. That's another cool thing about homogeneous is it saves me one column at least of work, right? So let's break this down. Okay, the first thing I'm going to do, so this is again with the row reduction, 2, 5, my little 1, 4. I'm going to multiply this column by 3 and add it here. So that's gonna give me 0, 1, minus 3, 0, 1. And I'm gonna multiply this first row by -4 and add it here. So that's gonna give me -1, 0, -1. That's gonna be -4, so that's gonna be 4. That's gonna be 0. And that's gonna be -1. Everybody okay so far? By the way, at this point, can you all predict how many pivots we're gonna get? What do you think? I see one for sure, but. I think we're gonna get 3, right? This one's gonna persist to be a pivot right here, and then I'm gonna get another one down here, it looks like. Okay, in this step, I'm gonna take this middle, I'm gonna take, this is, notice I'm clear here. I'm gonna take this 1, and I'm gonna clear out above and below. All right, so I'm gonna multiply up here by -2. So my middle row is gonna be the same, 0, 1, -3, 0, 1. Multiplying by -2, I get 0, 0. That's going to be 11. That's going to be still -1, and that's going to be 2. Tell me if you see me making mistakes, but that seems to be okay. And multiply, well, just straight up, I'm just going to multiply this by 1. So basically, I'm just going to add this. So that's going to give me 0, 0, 1, 0, 0. And actually now this is pretty, so I'm clear here. And now I've just got this one more pivot. All I gotta do is clear off up here. Because I am going for row reduced echelon form. I'm gonna use this one to clear this 3. These are all zeros, so it doesn't interfere with anything else. And I'm gonna use this one to clear that 11. And again, it doesn't interfere with anything else. And this should give me the solution to this homogeneous that I've got up here. But that looks like I got it right. So let's write down just kind of a vector thing for the solution of this. How many basic variables do I have? Basic. I've got 3 basic, right? Each for the pivots, because I got 3 pivots. And that leaves me what, 2 free, right? So I get X4, X5 are free. And I get X1, X2, X3 are basic. Which means basically that my basics should be written in terms of my frees. So let's kind of see what these equations say for us. X1 minus X4 plus 2X5 is equal to 0 because this is homogeneous. And this one is X2 plus X5 is 0. And this one is X3. What's the last one?
X3 is 0.
X3 is 0. That's right. So no matter what in this, my X3, it always has to be a 0. These first 2 allow me to write the other 2 basics in terms of the frees. And X2. So the solution, if I lose my place, I like to just kind of naively do this. Now let's make this better. What do I know? Well, X5 is free, so that's all I can do. It's just X5. It's one of my parameters. X4 is 3, is free. So there we go. What was X3? 0. It was 0, always. So my vector's always got that little zero right there in the middle. X2 is minus X5. And X1 is X4 minus 2X5. Notice, by the way, this allows me to write it this way. So I have X4 minus 2X5 minus X5, 0, X4, X5. Notice I can also write this X4 times 1, 0, 0, 1, 0 plus X5 times minus 2 minus 1, 0, 0, 1. Everybody see how I pulled it apart this way? Right, okay, on how I pull this apart. Because if you put this back together, you get X4 minus 2X5 in the top. So I pull this apart with the X4s in one and the X5s in the other. Everybody okay with it? Okay. Any questions on that example? Okay, let's do this. Another example here. Let's see here. Let's do this. Let's solve this system. Uh, 2x minus 2 y minus 2z equals 2. I'm sorry, that should be a 7. And 5x plus 2y plus 5z is equal to 4. Okay, so this one is not homogeneous, right? Because these are not zeros. They're not, they have to all be zeros on that side to be homogeneous. And so it's not even clear, is it, that this is consistent? This may have no solution whatsoever. So let's make a matrix here. 1, 1, 3, augmented. 2 minus 2 minus 7. And 5, 2, 5. Minus 1, 2. Now this one's not too bad. You could have done this days ago, but I want to kind of think about it as we tear this one apart. What do you all think? Is it going to be consistent? Is it going to have only one solution? Is it going to have several solutions? Let's see if we can tell where's the first place as we go along with our computation. The first thing I'm going to do is I'm going to use this to take these out. So I'm going to multiply this by -2. So I'm going to persist with having this. Multiply by -2, and I get 0. I'm going to get -4. And I'm going to get negative awful minus 13. Right? And that's going to be a 4. Everybody agree with that? Okay. Now I'm going to multiply this by -5 to take this out. That's 0. That's going to give me a -3. That's going to give me a, this will be -15 plus 5 is -10. And that's going to be 5 and 3 is 8. Now I'm pretty sure I've got a solution. Can anybody tell me how I can tell?
You have one pivot.
How many pivots am I gonna have?
Oh,
I'm gonna have a pivot in every row, right? This is a 3 by 3 matrix. If I've got a 3x3 matrix and I've got three pivots, then I've got a pivot in every row. Everybody agree with that? That means that, in fact, it didn't matter that this is -1, 2, and 3. Anything has a solution. That's what that theorem says. If I have a pivot in every row, I'm going to be able to solve this, right? So here I am pretty sure that I'm going to be able to solve it. Now the question is, do I have one solution or infinitely many? Suppose I have a 3x3 matrix, and suppose we've all agreed on the fact that this has got a pivot in every row. It also has a pivot in every column, right? Everybody agree with that? So how many free variables?
None.
None. So I bet there's a unique solution to this. Let's persevere. I'm going to take an extra step that you really don't have to take. I don't want to do it. I could multiply 1/4 and just by 1/3 to get ones here, but I'd rather not equal turpentine. Like I'm gonna basically multiply that -1 and add it here, so I'm gonna get a 1 almost. If I multiply this by -1 and add it here, then this is going to be -1, -3, -4. And now I don't have to deal with those crazy fractions, right? Because I can use this -1 to take things out. Okay, so I'm gonna have 1, 1, 3 -1. I'm gonna change the sign of this middle one because I can change the sign of any row. And also, I'm gonna multiply, or I'll change the sign, I guess. I'm gonna multiply that by -3 and add it here, giving me a 0, 0, and that's gonna be a -1. Multiply this by -1 and add it here. Or, I'm sorry, that was -3, wasn't it? So that's going to be 12 and 8 is 20. At this point, I could back substitute, right? Um, Over. I could back substitute because now I know that z is -20 and I can use this. Well, I'm gonna shortcut this a little bit. If I continue to do this, I'm gonna do this rather fast so we can fix from the middle for another one. This is going to be 0, 1, 0. That's going to be 64. And that's 4, so -5. So you can check me on this. The solutions are -20. Everybody okay with that? Any questions on that? Okay, perfect. I think we've got time. I'm gonna do one big system here. So x1 plus 2x2 plus 3x4 plus 5x5 minus 2x6 is equal to 2 x1 plus 3x2 minus x3 plus 4x4 plus 4x5 minus 3x6 is equal to 1. 2x1 plus 5x2 minus x3 plus 7x4 plus 10x5 minus 5x6 is equal to 3. And finally, minus 2x1 minus 3x2 minus x3 minus 5x4 minus 11x5 plus 4x6 is equal to 7. I don't even know if this is consistent or not. But so this one right here is, and I'm going to pick this one apart here. Let's get the matrix going. This is 1, 2, 0, 3, 5, minus 2, 2. 1, 3, minus 1, 4, 4, minus 3, 1. 2, 5, minus 1, 7, 10, minus 5, 3, and minus 2, minus 3, minus 1, minus 5, minus 11, plus 4 is equal to 7. Okay, so let's start taking this thing apart here and see what we can get out of it. I'm going to use the top row to take out everything under it. 1, 2, 0, 3, 5, minus 2, 2. Multiply this by negative 1. Take this out, and I'm going to get 0, 1, minus 1, 1, minus 1, minus 1, minus 1. Okay. Multiply the first one by negative 2 to take out the third row. 0, 1, minus 1, 1, 0, minus 1, minus 1. And finally, I'm going to multiply the first row by positive 2 and add it to this. Take that out. I want 0, 1, minus 1. Oh, this is working out nice. 1, minus 1, 0, and this will be 11, I guess. Now, I'm in a lot of luck here because there's a lot of similarity here. I'm going to use this to take out the stuff below it and above it. So 0, 1, minus 1, 1, minus 1, minus 1, minus 1. I'm going to multiply this by negative 2 to take out the 2 above it. So my top row is now going to be 1, 0, 2, 1, 7, 0. Multiply that by negative 2 and add it here, negative 4. Are you okay with it? And I'm going to multiply this by negative 1 on both of these right here. Take them out. And this is going to give me a long string of zeros. I'm going to have 0, then I'm going to have 1, 2, 3 zeros. And then 1. And then another 0. And then another 0. Boy, I'm digging that row for sure. And here, I'm going to have another long string of zeros. 0, 0, 0. Now it's going to be negative 1. Oh, whoops. Might be wrong one. 0, 0, 0, 0, minus 1. And then that's going to be 12. Everybody okay so far? Okay, so here I can use this to clear it up. Now I'm going to take several steps at once, and I'm going to show you the final row echelon form. when you clean this up with a couple more steps, this is the final form you get. 0, 1 minus 1, 1, 0, 0, 11, 0, 0, 0, 0, 1, 0, 0, and finally 0, 0, 0, 0, 0, 1, 12. That's what you get if you take a couple more steps after that last one that we did kind of longhand. So what do we have here? We have x1, x2, x4, x5 and x6, basic, and x3, x4, free. And so basically these equations are x1 plus 2x3 plus x4 equals 4, x2 minus x3 plus x4 is equal to 11, x5 equals 0, and x6 equals 12. So I'll write down what the solution is. If you write this out as x1, x2, x3, x4, x5, x6, this is x6 is 12, x5 is 0, x3 and x4 are free, x2 is 11 plus x3 minus x4, and x1 is 4 minus 2x3 minus x4. And I'll write this one more way, and I'll show you how to figure things out. Pull all the constants out. 4, 11, 0, 0, 0, 12. Those are all the numbers I find. It's just, they've got this 4 and 11 and 12. Plus x3 times minus 2, 1, 1, 0, 0, 0. Plus x4 times minus 1, 0, 1, 0, 0. This is a particular solution, and these over here, this is the solution to the homogeneous. Homogeneous, and this is a particular solution. So this solves a system that's the homogeneous, and every solution is this thing plus some combination of those. Okay, any questions? Yes.
So is there only one particular solution for regardless?
That is a great question. And the answer is no, because I could take this particular solution and add any multiple of this and this and make a new particular solution. You replace these with different variables and you're good to go. So actually, you might get different particular solutions. Others? All right, I'll see you on Friday.